Welcome to the debate. In late 1957, if you took a pencil and just gently tapped the metal casing of the world's most advanced computer transistor, the entire system would fail.
Just from a tap.
Literally just a tap. And yet today, we are detouring massive cargo ships full of liquid helium thousands of miles out of their way just to keep our artificial intelligence infrastructure from literally melting down. So how did we get here?
It is a massive leap, isn't it? I mean, going from a fragile little speck of silicon to a global supply chain that's basically teetering on the edge.
It really is. To understand the sleek, frictionless digital world we live in today, we have to look back to a very grounded moment in late 1957. 8 brilliant engineers, famously known as the Traitorous Eight, fled the erratic mismanagement of William Shockley's laboratory.
Right, to found Fairchild Semiconductor.
Exactly. That single defection effectively birthed Silicon Valley. But it leaves us with a profound, unresolved question about what fundamentally drives this digital revolution.
Right, like are we looking at a history driven by human imagination or one dictated by the periodic table?
Exactly. Is this industry propelled by the sheer conceptual brilliance of architectural engineering, specifically visionary leaps like Jean Hoerni's planar process? Or is the digital age ultimately dictated by the grueling, unavoidable mastery of physical materials and chemical supply chains?
The bricks versus the blueprint.
Right. And I argue that visionary architectural breakthroughs are the definitive engine of the semiconductor industry. It is the architectural blueprint that forces matter to obey.
Well, and I contend that mastering finite material and chemical constraints is the true driver of this industry. The history of semiconductors is not a story of pristine architectural genius, It is a story of industrial brute force and terrestrial limits.
So you're looking at the raw materials.
Absolutely. That is a reality proven by the agonizing early days of silicon manufacturing and undeniably confirmed by the crippling 2026 global helium crisis. The blueprint is entirely useless if you cannot physically manipulate the elements.
Let's start with the blueprint, though. To understand the power of the architectural leap, we really have to look at the state of technology before Jean Hoerni.
Okay.
Hoerni was a Swiss physicist, a brilliant theoretician. At the time, the industry standard was the mesa transistor. It physically looked like a microscopic southwestern mesa, a little plateau of silicon.
Right, I've seen the diagrams.
But it had a fatal design flaw. The vital PN junctions were left completely exposed to the outside air.
And for our listeners, we should probably clarify what that junction actually does.
Yes, good point. Think of a PN junction as a microscopic turnstile, or maybe a valve that controls the flow of electrons.
It's where the electrical magic happens?
Exactly. But because it was exposed on the mesa transistor, it was incredibly fragile. I mean, a single speck of dust would short it out.
Bell Labs' conventional wisdom dictated that the silicon oxide layer, which naturally formed during manufacturing, was dirty and had to be stripped away.
Right, like peeling a rind.
Yeah. It was essentially viewed as the messy scaffolding of a building that you tear down once the structure is finished.
Which seems logical. I mean, you don't want construction debris on your finished product, right? But Hoerni defied that. He conceptualized leaving the oxide layer on. He realized that this so-called scaffolding could actually serve as a permanent protective roof over those sensitive electron turnstiles.
The planar process.
Exactly. It created a flat or planar topography. That single conceptual design shift is the foundational architecture of the modern world. It's what enabled Robert Noyce to invent the integrated circuit. And it's the strict mathematical premise that made Moore's law possible.
The consistent doubling of computing power.
Yes. Without Hoerni's specific architectural insight, the digital age stalls before it even begins.
I mean, that is a beautiful, very neat, great man narrative. But it completely ignores the brutal reality of the laboratory floor.
How so?
Well, I come at it from a different way. You say he bypassed the material fragility, but Hoerni wrote that idea down in a notebook in December of 1957. And you know what happened?
I mean, it sat there.
It sat there for over a year. It was completely useless. Why? Because the real breakthrough in semiconductors isn't the drawing. It is the chemical execution.
The manufacturing.
Right. When Jay Last's team at Fairchild finally tried to make an integrated circuit based on these ideas, They were battling what Bell Labs called the tyranny of numbers.
And the tyranny of numbers was basically the statistical wall of hand manufacturing, right?
Exactly. Before the integrated circuit, you had to hand solder thousands of discrete components together with tiny wires. If you have a computer with 100,000 soldered joints and even a 1 in 1,000 failure rate, every single computer you build will fail.
So it was a statistical impossibility to build complex machines.
Yes. So to solve this, Fairchild tried to build everything into one block of silicon. But they had to invent savage brute force methods just to make the silicon yield. They were literally etching entirely through silicon wafers, mounting the fragile remnants upside down on glass plates, and enduring grueling 18-hour boron diffusions.
Well, the boron was used to physically isolate the different components on the chip.
Yes, but boron was a chemical nightmare. Those diffusions were so chemically violent, they softened the glass tubes of the furnaces.
Wow.
Yeah, and it physically pitted the silicon oxide layer. My point is, architectural genius is an illusion if you cannot tame the violent chemistry required to build it. The industry is, and always has been, bounded by the limits of the physical earth, not the limits of the human mind.
That's an interesting point, though. I would frame it differently. Because you cannot tame the chemistry without the theoretical framework telling you what to tame.
Okay, fair.
Let's look closer at Hoerni and the planar process. His colleagues described him as Gallic, charming, temperamental, and intensely competitive. He was reportedly most innovative when he was angry.
An angry physicist?
Exactly. He wasn't a tinkerer, he was a physicist who trusted the math. The real genius of the planar process wasn't just leaving the oxide on, it was understanding how the chemicals behaved underneath it.
You're talking about isotropic diffusion.
Yes, exactly. Hoerni realized that when you diffuse chemicals into silicon, they don't just drill straight down, they bleed outward, like a drop of ink expanding on a paper towel.
Right, the sideways bleed.
Because of that sideways bleed, the sensitive PN junction formed underneath the protective oxide layer. It tucked itself safely under the roof. It was an elegant, counterintuitive mathematical leap that bypassed the material fragility of the MESA transistor entirely.
But the manufacturing reality was still a nightmare of contamination and physical failure. Yes, Hoerni understood the isotropic diffusion, but actually making a planar transistor required 4 masking layers instead of 3.
It was more complex.
Much more. The team wasn't set up for that. When they finally did attempt to build the integrated circuit, the physical isolation of the components was nearly impossible. You mentioned the elegance of the math. Well, imagine designing a brilliant architectural arch, but the only mortar you have melts the stone. That was the boron problem.
But wait, if the boron was literally melting the glass tubes and destroying the equipment, how did they ever get a working prototype out the door?
By fighting a grueling war of attrition against the elements. Just 15 minutes of diffusion would start destroying the equipment. But they had to run it for 18 hours to get the isolation deep enough.
18 hours.
Right. It wasn't an elegant redirection of force. It was sheer industrial stubbornness until the production engineers finally figured out how to use a different chemical compound, methyl borate, to keep the furnaces from literally dissolving. The architecture was failing until the chemistry caught up.
Right. Well, even in the midst of that grueling manufacturing process, theoretical calculations were required to solve the physical problems. It wasn't just trial and error. Consider gold doping.
Oh, the gold doping paradox.
Right. At the time, the entire industry considered golds to be the absolute nemesis of semiconductor manufacturing. It was known to kill the lifetime of electrical carriers in the silicon. It was basically poison to a microchip.
Complete poison.
But Hoerni did the theoretical math. He calculated that you didn't actually need that much lifetime for the transistor to function as a simple switch, and if you introduced gold, it would cause the carriers to return to equilibrium faster.
Which significantly sped up the switching time of the transistor.
Precisely, and furthermore, it created a serendipitous gettering effect. The gold physically cleaned up the junctions by pulling away stray impurities.
Right.
He took a known chemical poison and used theoretical physics to turn it into an ASIC. And this brings me to the scaling of the integrated circuit. The transition from discrete single transistors to a complete monolithic circuit was, again, a triumph of design over material.
How so?
Well, Robert Noyce looked at Hoerni's planar process and saw that the flat oxide layer allowed conductive metal lines to be evaporated directly onto the surface. No more microscopic hand soldering?
But evaporative metal over oxide doesn't automatically mean you have a viable product.
It does when paired with strategic design. By 1964, the integrated circuit was largely a commercial failure. It was considered a boutique military novelty because a single logic gate cost $150, whereas you could build the same thing with discrete components for $3.
A massive price gap.
Massive. But Noyce solved this, not with brute force, but with a brilliant commercial and architectural strategy. He decided to sell the integrated circuits below what it cost Fairchild to make them.
Which is insane.
It sounds insane, but he trusted the inherent mathematical economies of scale within the planar architecture. He knew that if he stimulated volume, the process would eventually become so mathematically efficient it would cover the cost. It was a staggering bet on the superiority of the design.
I'm sorry, but I just don't buy that. Let me tell you why. Noyce's pricing strategy was a massive gamble that only paid off because of the underlying batch processing ecosystem that Fairchild had painstakingly built.
But the ecosystem was based on the design.
Sure, but they weren't just printing perfect mathematical models. The material scientists were fighting and winning a daily war against catastrophic chemical failures. Have you looked at the failure modes of early ICs? They were plagued by something called purple plague.
Wait, purple plague? Are we talking about some kind of literal biological contamination in the clean rooms?
No, it was an intermetallic degradation. They were using gold bonding wires attached to aluminum metallization on the chip. Under the heat of operation, the gold and aluminum reacted and formed a brittle, purple-colored compound.
Oh, interesting.
Yeah, and this compound was so fragile that the connections would physically snap. And if it wasn't the purple plague, it was the electromigration of aluminum.
Where the electrical current physically moves the metal, right?
Exactly. We think of electricity as weightless, but when you cram that much current into a microscopic aluminum wire, the force of the electrons literally pushes the aluminum atoms out of place.
Wow.
It creates microscopic voids that eventually sever the wires. The architecture was beautiful on a whiteboard, but in the physical world, the atoms were literally tearing themselves apart. The design was entirely hostage to whether or not the metallurgists could invent new alloys and barrier layers to stop the physics from destroying the chip.
I don't deny the severity of electromigration or intermetallic compounds. But look at the historical trajectory here. Whenever the industry hits one of those terrifying material limits, architectural ingenuity bypasses it.
Bypasses it?
Yes. When the original bipolar transistors reached their physical limits for scaling, meaning they got too hot and leaked too much power, the industry didn't just stop. The engineers shifted the entire paradigm to MOS technology.
Metal oxide semiconductors.
Right. They changed the architecture entirely. MOS transistors act like static gates. They only use significant power when they actually switch states, which drastically reduces the heat. The foundation laid by Hoerni and Noyce proves that human engineering design will always find a way to route around a physical roadblock. The constraints simply force the architecture to become more clever.
That's a compelling argument, but have you considered what happens when the physical roadblock is absolute?
What do you mean?
We just jumped 50 years of scaling history. We are so used to this narrative of engineers triumphing over atoms that we've blinded ourselves to hard planetary limits. You want to talk about extreme scaling and bypassing physical constraints? Let's look at the logical extreme of that scaling today. Let's talk about the 2026 global helium supply crash.
Right, the geopolitical crisis.
It is much more than geopolitical. It shatters the illusion of limitless engineering. When the military strikes hit Qatar's Ras Laffan industrial city, the global technology ecosystem fundamentally fractured.
Because of the natural gas disruption.
Right. But Ras Laffan wasn't just a natural gas plant. It was the undisputed center of global helium production. Up to 38% of the world's usable helium vanished overnight. And here's the brutal reality. You cannot engineer helium in a laboratory.
It's just a byproduct.
Exactly. A strictly finite byproduct extracted in tiny trace amounts during the processing of liquefied natural gas. When that physical supply was severed, no amount of architectural brilliance could save the fabrication plants.
But again, Isn't that a logistical supply chain crisis? I mean, supply chains adjust, ships get rerouted. How does that prove a failure of semiconductor architecture?
Because it is a chemical choke point that dictates whether the architecture can exist at all. Modern fabrication plants run on ultra-lean logistics. They typically hold exactly 1 week of helium inventory on site.
Just 1 week?
1 week. And when the Persian Gulf routes closed, the remaining maritime cargo ships had to detour 3,500 nautical miles around the Cape of Good Hope. Do you know what happens to liquid helium on a 44-day transit?
It boils off, doesn't it, if it breaches the thermodynamic window?
Exactly. To move liquid helium, you have to keep it at minus 268.9 degrees Celsius.
Barely above absolute zero.
Right. The specialized cryogenic containers are incredible pieces of technology, but they can only hold that temperature for 45 to 48 days. That detour around Africa pushed them right to the absolute physical limit of their insulation.
So they lost the cargo.
Ambient heat breached the containers, the liquid boiled back into a gas, and up to 15% of the cargo had to be literally vented into the atmosphere over the ocean just to prevent the tanks from exploding.
Wow. But surely, a design-focused mind would just look for a substitute. If helium is that volatile to transport, why not use a different gas in the manufacturing process?
Because you hit a hard chemical wall, you literally cannot substitute it. In a modern plasma etching chamber, which is what we use to carve these microscopic AI chips, you are generating intense, incredible heat.
Okay.
If you try to cool that wafer with nitrogen, the nitrogen traps the heat and ruins the silicon. If you use hydrogen, it cools efficiently, but hydrogen is highly explosive and an electrically charged plasma. Helium is the only inert noble gas that can safely transfer that massive heat without detonating or destroying the chip. It is irreplaceable.
I'm not convinced by that line of reasoning because it drastically underestimates the adaptive capacity of the industry. Yes, the helium choke point is a severe, terrifying crisis. It forced factory managers to run their tools below optimal settings. It increased defect rates. It caused massive back orders for advanced microchips.
Total chaos.
Exactly. But look at how the industry is actually responding. It isn't just shutting down.
Well, they are rationing gas.
They are rationing, yes, but they are also initiating another massive wave of engineering innovation. Fabrication plants are now spending millions to install cryogenic distillation, rebreathers, and membrane separation systems right on the factory floor.
To catch the waste gas.
Exactly. They are creating internal circular economies, capturing the exhausted helium gas, scrubbing out the impurities, and recycling it. The physical boundary hasn't stopped the industry. It has simply dictated the shape of the next architectural breakthrough. The design focus has just expanded from the microscopic circuitry of the chip to the macroscopic circulation of the factory itself.
But don't you see, that proves my exact point. The fact that multi-billion-dollar fabrication plants have to install massive industrial rebreathers just to squeeze a few more cycles out of a captured trace gas shows that terrestrial chemistry is the ultimate master here. Look at extreme ultraviolet lithography, EUV.
The lasers used to draw the smallest transistors?
Right. This is the light-based process required to carve the sub-5 nanometer chips running the entire AI revolution. The EUV system demands a continuous helium purge.
To protect the optics.
Yes, it constantly flushes the multi-layer optics with helium to sweep away stray hydrocarbon molecules before the light beam can crack them apart and leave microscopic carbon smudges on the mirrors. Even high-capacity data storage drives have to be hermetically sealed with helium just to reduce the aerodynamic drag on the spinning platters inside.
It's everywhere in the process.
By 2030, the tech sector's demand will hit 30% of the entire global supply. We talk about the boundless virtual potential of artificial intelligence, but every single computation is tethered to a non-renewable gas trapped in ancient underground rock formations. Architecture is entirely subordinate to geology.
I hear your point about the immutability of these elements, but I look at the historical sweep of this, from Gene Hoerni in 1957 to the EUV lasers of today. Hoerni stared at a fragile, failing mesa transistor and realized that the very oxide layer everyone thought was useless contamination was actually the key to protecting the entire system.
He flipped the problem.
Right. He reimagined the physical reality through conceptual design. The planar process, Noyce's integrated circuit, the transition to MOS, these are blueprints that forced material reality to bend to our will. Even now, with the helium crisis, the response is fundamentally architectural. The rebreather systems are a design solution to a material deficit.
A very expensive design solution.
True, but the digital world is primarily a product of human ingenuity. We don't just accept the limits of the rocks and the gases. We structure them, we design around them, we integrate them into systems of unprecedented complexity.
And I look at that exact same history and see a continuous, exhausting war of attrition against the physical Earth. The blueprint is a dream until you get your hands dirty.
Fair enough?
From JLAS's team enduring 18-hour boron diffusions that melted their equipment, to the metallurgists fighting the purple plague and electromigration, all the way to modern supply chain managers desperately trying to capture venting helium over the coast of Africa, the semiconductor industry is fundamentally bounded by terrestrial chemistry. We extract microscopic trace gases and battle the laws of thermodynamics every single day just to keep the illusion of a frictionless digital world alive. The genius is necessary, sure, but it is the physical Earth that sets the absolute speed limit.
It is a profound intersection. I mean, we are manipulating the building blocks of the universe at an atomic level. It requires both the abstract equations written in John Hoerni's notebook and the brutal extraction of trace gases from beneath the Earth's crust.
It does. It requires both the visionary architect and the gritty mechanic fighting the laws of physics.
The next time you pick up your smartphone or ask an AI a question, consider what you are actually holding. You are holding a mathematically perfect architectural concept built inside an invisible atmosphere of ancient, finite gas. It's a fragile, breathtaking balance of genius and geology. Thank you for joining us on The Debate.